thank you so much. I know you flew out to be with us today. It means the world. We've been getting to know your team for years. Kimberly, Rory, Anthony, the whole team. They're just incredible. Yeah. And it means the world to us that you're out here to talk about biology with us today.
This is my team. I think this is the largest investment we've ever made outside of our company.
Well, thank you. That means the world. When we were speaking last, you talked about, at the beginning of your career, how the silicon chip industry was laboratory-based, empirical-based, and you saw it transition to entirely in silico, or almost entirely in silico. What lessons can we learn in the biology field from that transition? Are there parallels? Can you talk a little bit about that?
There are absolutely parallels. And this is my career started 40 years ago, 41 years ago. And it was right at the time when computer-aided design started to make progress. Not that people didn't talk about computer-aided design before. It was just the combination of algorithms, computers that are fast enough, and know-how. Now that know-how was described as, and introduced this word into modern chip design that was really, came out at that time. And that word is called methodology. Until then, nobody used the word methodology. And methodology was inspired by Mead and Conway. I don't know if you guys have ever seen that, read that book, but it was written by a professor at Caltech. And anyhow, two of them, Mead and Conway, wrote this book to describe how you could create using very simple methodologies. It was based on first principles, but ultimately simplified the chip design methodology that enabled the creation of very large chips. And it's a book about VLSI design, VLSI systems. The concept that finally chips were able to be sufficiently large and complex that you could capture entire systems within it. And so they described methodologies for designing, for laying out the transistors, and how to simulate it, how to scale it. Mead and Conway's book really inspired a whole generation of chip designers. So the three things came together: algorithms, and now this is happening in your industry. Computing, this is happening in your industry, and know-how. And these three things, of course, in the case of chip design, the know-how doesn't as much involve the amount of data that your industry requires. But if you look at the foundation of recursion, these three things are at play. The invention of a new algorithm, or new family of algorithms that we call deep learning, supercomputing capabilities that you've used here, and that we partnered with you to create. And of course, this know-how from robotics laboratory to generating and systematically generating data to learning from it, all of the multimodality nature of biology, and the know-how of processing, extracting the meaning of biology that's embedded within life, within that data. And so this know-how, this combination of all these things are happening right here. But I had the benefit of seeing it for the very first time in chip design 40 years ago. And the amazing thing is my manager spent all of his time in the lab. I was the first generation that was comfortable in the lab and not in the lab. We don't have a chip designer today that spends any time in the lab. They never go to the lab. The only reason to go to the lab is really just for the party. You know, the chip came back and it's working exactly as we expected. Now, you have to imagine this. 10,000 engineers work together for 3 or 4 years at a time. They take all of their work, they put it into one chip. That chip comes back in a massive system thousands of these chips together, a whole lot of different types of chips, and we turn it on. It's an insane idea. And on the day that the computer comes alive and is working, it's not a miracle to me. It's fully expected to me. In fact, it's just another day in the life of that chip. And the reason for that is because that chip has existed for a long time in silico. For a long time, it's been doing the job that it was intended to do and it was just doing it inside this chip is doing it all inside another chip that we had built last time. And so you got these inception levels, chips that are creating next generation chips so that we can design algorithms to design next generation chips.
Recursive in that way.
Yeah, exactly. It's recursive in that way. It's almost like recursion. But that's it. That was my generation. I got to see it.
Did it feel inevitable at the time to you, to everybody else, that progression, or did it not?
Most people at the time would tell you that it will never work, and the reason for that is because the corner conditions, all the long tail of problems, and all the pain and suffering that they endured in the laboratories, and all of the chips that came back completely non-functional, their life experience caused them to not believe it's possible. And I think the journey of almost every industry is kind of the same. That the early people who made that industry suffered so greatly and things worked so poorly that by the time that it was ready to work well, they don't believe it. It can't possibly be that easy. Now, there's nothing easy about it, of course. It's just that the learnings were codified into tools. And in our case, and this is the part that's hard for you, and the reason why it's taken so long. In our case, we can change our, if you will, our transistors are, the minimum unit of our biology, okay? And we could change the structure of the transistor until we could design with it. You can't. Your transistors you have to live with. They are what they are. Our transistors, we shape them until they behave the way that we expect, or that they fit within the distribution of the capabilities of our simulation capabilities. And so if we can't predict how a transistor or a chip behaves in these corner conditions, well, don't go there. That was the easy thing. We shift our design rules. That's why we have these things called design rules. You don't have design rules.
Unfortunately.
Life is the rules, and evolution is the rule that you live with. We have the opportunity to shape our transistors and our chips to the point where it turns out our transistors are so small now, they're statistically different. And if one transistor is pointing this way, another transistor is pointing this way, they behave slightly differently. Well, the answer is very simple. Make them all point the same way. And so we cause our chip designs to do things so that they behave according to things that we understand until we could push the limits further. And so otherwise we have these things called design rules and methodologies, and then everything kind of fits within it. Your challenge is much harder because you have to learn the behavior. You have to learn the meaning, the behavior, the properties of these biologics just the way they are. And well, the good news is finally you have the technology necessary to do that.
That's right.
I think we, within our grasp, it surely feels that between the robotics laboratories that you're creating for data process, data collection, systematic data collection, and machine learning, and the supercomputers that we build together, you might be within a click or two away from really being able to understand the meaning of life.
That's a tall order, but we're working on it.
Yeah.
When you look at problems to approach at Nvidia,
You're kind of like where the first yellow.
Where the first yellow
is,
holds?
yeah.
Okay.
You're close.
For those who can't see, that's almost to the top of the wall. For clarity, for the investors
That's
in
where
the
you guys
audience.
are. First.
you are one of the few companies that gets to work across every industry, basically.
Yeah.
When you look at your stance in healthcare, I've heard there's sort of 3 rules. You ask whether a problem is hard, you ask whether Nvidia can make a unique contribution, and you ask whether that will be impactful. I think it's easy to imagine that life sciences, healthcare is hard. It's easy to imagine it's impactful. What is the unique contribution that Nvidia can make in the context of healthcare? What is your stance on healthcare broadly, beyond recursion, just zooming out?
Yeah. Well, the 3 things that I said, just to flip it on its side, the alternative is go do something better that somebody else has already done. Pursue a path that leads to the fastest ROI. And so these are the characteristics of people who love to win and make a lot of money fast. And there's nothing wrong with that. There's nothing wrong with any of that. But that's not us. Our personality is to go do something nobody's ever done before. Do something that if we didn't do it, nobody's going to do it. And 3, if you choose well, not only will you enjoy the journey, you can make a real contribution. And you might be able to live a life of purpose. And so that's kind of in our DNA. That describes what NVIDIA is. It describes the way I talk to the company, the challenges we select, the way we approach opportunities and threats and challenges and things like that. And so I think that's in our DNA. Now, the problem, of course, of understanding the language of life and to be able to do drug discovery in silico, if that's not a hard challenge, I'm not sure what is. I mean, that's an insanely hard problem. However, it's within our lifetime to do something about it. And as you know, earlier we were saying that there are 3 ingredients. There's the ingredient of the algorithm, there's the ingredient of computing, and there's methodology, which in a large scale is kind of domain expertise. Notice we could contribute to 2 of those 3 things in a pretty profound way, in a really deep way. And because we don't have that domain expertise and we don't desire to have that domain expertise, we could be a great partner to somebody. We want to help every car in the future to be as autonomous as possible so that it can be as safe as possible. But we don't want to be a car company. We would like AI to advance as safely and as quickly as possible, as capable as possible. But we really don't want to host and provide a large language model service. And so notice in many domains and many industries, as you called it, we don't want to be the industry leader. We want to enable the industry to have leaders, and so that we could focus on our unique contribution. And so I think that we could play a really great role at that intersection in the three pillars that we mentioned. And you have such deep domain expertise, you have such passion for the methodology, and you have a pioneering spirit. You want to go make this happen. And so I love people like that. I love endeavors like that, and I love you guys because of it. I think it's great.
Jensen, speaking of partnership, we built together BioHive 2. Our team was sleeping on the floor of the data center to get this thing stood up in 3 weeks, and your team was too. So kudos.
Where I stopped listening was, I was going, huh? Our teams were sleeping.
They were working hard.
My internal knee-jerk reaction went, huh?
No sleep. We stood that thing up in 3 weeks.
Uh-huh.
And it is now the fastest supercomputer in biopharma. Is it surprising to you that the fastest supercomputer in biopharma is being built and operated by little Recursion and not one of the massive biopharmaceutical companies?
Is it actually in here? is in Dick's
No,
sporting
no, no.
goods
The supercomputer, we thought about hanging it from the ceiling, but ultimately we had to move it to a data center down south, a few miles away.
When I walked in, I was thinking, now it makes sense. This is where our supercomputer is. Nvidia was the first chip company to build supercomputers for our own use. Turned out to have been a good decision. Tesla is the first car company to build supercomputers. Not a bad call. Lots of other examples. The simple idea is whether you believe, whether we believe, whether a company believes that in order to discover knowledge out of something where principled simulations will simply not get us there. Remember, there was a time when we thought molecular dynamics with enough supercomputers, we're going to simulate the human body. We kind of gave up on that idea. We have a better idea. Isn't that right? And so there was a time where we thought, surely there was a time when I thought, that we're going to have supercomputers large enough to be able to do weather simulation to the minute to every region in the world within, kilometer or a few hundred feet. It's now very clear that that's not going to happen. That even with NVIDIA's accelerated computing systems, it'll still require something a billion times larger, and a billion times larger is still a few decades away. And I'd like to see it in our lifetime. And so the way we solve that problem, and just to give you an example, in our world of computer graphics, we do this thing called ray tracing. And we thought ray tracing was still going to be 3 decades away. 3 decades away. Today we path trace, which is more advanced than ray tracing, everything. And the way we solved that problem, and the performance is incredibly good, and the way we solved that problem was we simulate 1 pixel, and we use AI to guess the other 64. Okay, and we're doing the same thing with climate. We understand the physics. You don't have to go brute force simulate the physics for every single protein and every single cell. And so it's very clear we don't have to simulate the physics. We understand the physics of weather. We don't have to go simulate the physics for every square kilometer. And so we could teach an AI how to predict physics and let the AI go and tell us what's going to happen. Not because we want to understand the causality of weather. We understand causality of weather. We just want to know what the weather is going to be like this afternoon. That's all. Do you understand what I'm saying? That's a fundamental difference. That's a giant mental leap. That's we understand the causality of things. We want to understand how it's going to impact a person or some disease or whatever. How do we cure certain disease? We probably understand the basic biology behind it. Of course, the complexity of multi-omics makes it hard. We understand biology. It's just that in the larger scale of things, it is so hard to understand its interrelationships. We now need to use some other type of algorithm to go understand it, which is AI. And so I think that if you believe in these things, these principles, then you've got to, and then the second thing is if you believe that your company is fundamentally about intelligence, that your company isn't producing drugs, you're producing intelligence that leads to the production of drugs. And if this is how intelligence will be amplified, intelligence will be discovered, intelligence will be amplified and put to use, then how is it possible that you don't have the instrument of intelligence? And so when you think through it through first principles, the people who are able to think like that are able to make that next leap. If this is to be true, even though nobody's ever done it before, if this is to be true, and you fundamentally believe in something, and even though nobody's ever done it before, it doesn't mean you shouldn't do it. This is exactly the reason why you should do it. And so that we reason about things, in this way, and I think I know that most pioneers and leaders innovators think in this way, and you guys think in this way. I think it's really terrific.
When you think back to how you thought that way 30 years ago, with the founding of Nvidia, we've got analysts, investors, patient advocates, and also many founders, and I would say probably among our employees here, some future founders as well. You faced a lot of skepticism, and yet the first principles told you the direction to go. How do you, as a founder, as an early employee, as a visionary and a pioneer, how do you have that faith to keep building across multiple decades in the face of all of that skepticism?
Well, first of all, we reason about things from first principles the best we can, and sometimes the first principles don't exist because we either don't understand it completely, and maybe there's a bit of a leap of faith. You just believe it. It must be so. And all of that belief or that reasoning came from somewhere, some external information or you're informed about it somehow. If the facts don't change, why change your beliefs? If the facts don't change, we're a universal function approximator. You and I were both this giant deep learning model. And if the input doesn't change, why should the output? And so I'm kind of wired that way. I challenge my reasoning constantly. In fact, almost literally every day. And I gut check on how we arrive at a lot of the assumptions that we arrive at, because of a lot of people are at stake, and a lot of the work that our employees do are at stake, and so you have to reason about these things, but you have to double check your assumptions all the time. If things don't change, why do you stop believing in what you believe in? So you got to believe in something, and so you want to be as informed as you can. You want to be as reasoned as you can. You want to go back to first principles wherever you can, and then lastly, there's always that leap of faith that is necessary for all great things to happen. If it was obvious to everybody, then it would have already been done.
Somebody's got to go do it.
Somebody's got to go do it. And so we believed in the first principles that general purpose computing, this universally general tool, can't possibly be the right instrument for every type of computing. And if you look at a CPU, for example, that ALU is doing the work. And that ALU is only a few percent. It's like a company where the engineer is doing the work only is like 3%. The other 97%, management overhead. Now, that's what general purpose computing is, and our first principles doesn't make any sense. And so we weren't trying to replace general purpose computing. We were thinking, there's a reason why CPUs exist, and we designed plenty of them. And it's good for whatever it's good at, but why don't we just augment it with something else? We call it accelerated computing. That's why we don't call it parallel computing. Parallel computing is kind of like, as opposed to sequential. The two of them you have code that's single-threaded, you have code that could be multi-threaded, And so we reasoned from first principles that if we were to figure out a way to get that to be the nature of computers, and every computer has those properties in it, and that there was a good programming model to deal with this kind of a complexity, then we can really change computing. And so we believed it from the very beginning. The question is, how do you find those applications? And we found one after another. The first one we found was computer graphics. That was a very sensible one. And then the next one was image processing, and then molecular dynamics, and particle physics, and fluids, and so on and so forth. And we just kind of kept finding our way there. And then one day we found deep learning. And so
it's incredible. Last question, because I know you have to go.
I don't have to go right now.
Okay. Then I've got 20 more questions.
Okay, good. Good. I'm happy to be here.
When we first met, 18 or 24 months ago, you told Ben and I something.
Chris is hosting all of you here. I need to fly back to host. I'm still working for a living too.
You told Ben and I that the natural state of every company was dying, or that every company was 30 days away from dying.
Yeah.
And that resonates deeply with probably every founder of a startup.
Yeah.
But hearing it from you, I think could be surprising to people, and probably is also because you feel that one of the reasons NVIDIA has been so successful. Where's that philosophy coming from, especially at the stage of company you are now, and what can all of us learn who are building earlier stage companies from that philosophy?
I just, I think Nvidia's a supremely confident company, and you have to be in order to do great things, but you can't be complacent. And so somewhere between confidence and insecurity, maybe that's what it is, is where we live. That we always believe that we could do amazing things, but if we don't keep doing amazing things, we don't get to do this anymore. And so when I wake up in the morning, and this morning is no different, all these thoughts of problems, that's the first thing that comes to my head is problems, and the problems that should have been solved last night that wasn't solved, and so I wake up to those, and so good morning, and the problems are challenging, and I consider them somehow, for some reason, I've always internalized them to be existential. That if you don't take care of these things, eventually you'll get bad, and everything will come to an end. And I felt that way in 1993. I felt that way this morning. I don't know how to. I think I need therapy. That's what it is. No, I'm just kidding. I don't think it's. I think it's good to be able to be a properly functioning adult. Both being confident you can achieve something incredibly hard that nobody's ever done before, on the one hand, and on the other hand, really having a sense that you have to keep working at it, and never be satisfied, and don't be complacent, and all of those feelings I don't think you want settling in, and so a long time ago, I used to share our financials. Well, I still share our financials with all of our employees. They're just public now. But back in the old days, I would share our financials with our employees every Friday. And I had a laptop, and I just put it up, and we're looking at a spreadsheet, and somebody said, so Jensen, that our cash runs red in June. I think it was June. And I said, yeah, if we don't make money before then, we'll be out of business. The second question was, what does that mean? The engineer asked, so what does that mean? I said, well, it just means that if we don't, make more money in 30 days, we'll be out of business. And then I literally just said what that means. I mean, that's what it means. I wasn't trying to judge or anything. I just said, hey, what does that mean? I said, in 30 days we'll run out of money. And then somebody else said, so what are we going to do? I said, well, don't run out of money. And so we have one of two choices. We can either make some, or we can go raise some. And I'm not sure we're good at either one of them at the time, and so I think one of the genuine possibilities is our company could go out of business, and we didn't. We always, somehow there's always a diving catch.
Spoiler alert.
Yeah, we didn't, and over time, I just want to remind people that if we don't do our jobs, we'll be 30 days from going out of business. And then all the employees that were there at the time told all the other employees that we have to really stay focused, because if we don't, we could really go out of business in 30 days. And then one day we had gone public, and we're having a company meeting, and somebody asked, Jensen, we heard rumors that we could be out of business in 30 days. And I said, hey, listen, if we don't do our jobs in the next 30 days, we could go out of business someday. So yes, we could be out of business in 30 days. And so all of the new employees just panicked. So, but anyways, I think your psychology should be that as a startup, every day matters. And I can tell you with great confidence, as a startup company, every day matters. And so the next 30 days, the decisions you make, the things that you do, the people you hire, the accomplishments, the culture you create, all of those things, all of those, they could lead to either you being vibrant, succeed for a little longer, or go out of business in 30 days. I completely believe that, and I believe it for me. And so.
Thank you. And the corollary, I think, to that in our industry is that we get to know some of the patients who we hope to one day be able to treat. And those patients are waiting, and so every day matters.
Every day matters, yeah. Every day matters.
That mission.
Yeah, every day matters. And look, we're volunteers. All of you are volunteers, 100%. 100% of you are volunteers. You don't have to work here. You don't have to work, for many people, you don't have to work at all. And so you surely don't have to work here, so you're volunteering to work here.
But please keep working.
No, yeah. You're volunteer to work here. You're volunteer to work. Nothing is stronger than the heart of a volunteer. You volunteer to work here. And the reason why you volunteer to work here is because you believe in the mission, you like the people, you enjoy the people, you believe you're doing something important, and so you get to do it every day. If suppose everything I said was true, then you get to do it every day. Why wouldn't you want to do it every day? So do it every day. That's the way to think about it. So instead of, it's not because we're obligated to work every day or, gosh, we got to do our best work today. We get to do our best work every day. And so I think you guys are, you're during just an extraordinary time in your industry. Yeah. And you're also going through an extraordinary time in industry. You have to realize that the instrument of your work has not been reimagined in 60 years. The year after my birth, IBM announced the System 360, the general purpose computer architecture that's remained largely the same until now. And all of a sudden, we created this thing called accelerated computing, and on top of that, a new computing model called generative AI, and it's changing completely everything. How software is written, how software is processed, the type of software we can write, the type of problems we can solve, for the very first time, completely revolutionary. It's changing every single industry. And so for us as an Nvidia, to be at the center of this industrial revolution, this computing revolution is extraordinary, but for you to be able to utilize this capability to revolutionize one of the most important industries of all, humanity. The timing is incredible. This is a once-in-a-lifetime opportunity for all of you. This is a once-in-a-lifetime company and a once-in-a-lifetime circumstance. And so if you could slam 2 days into one, I do it. So this is just such a fun time for you guys. I'm here to tell you I'm jealous. This is really, really great. I'm very proud of you.
We have an opening if you're interested.
What, do you have an opening as a patient?
I hope not.
Okay.
I hope not. So thank you, Jensen.
Yeah.
This has been amazing. Before we go, at GTC, your conference, a member of our team was wearing something very special, which was this rainbow GPU necklace, which you signed, and we have literally encased.
Wow.
And you asked us there to make you one, so we did.
Oh,
this
wow.
This is your rainbow GPU necklace.
Okay, I'll wear it.
And you also asked us to make 2 for your kids. And so, big thanks to Jenna and the team.
My gosh, thank you. Thank you so much. This is
it's an early architecture.
How many teraflops is this?
I don't know if
teraflops
Imran's here.
is
This
this?
is one of the earlier ones.
Okay, this is beautiful.
But big thanks. And would love, before you go, just to get a picture of you with everybody
I would love
here.
it.
Is that
I would
okay?
love it. Thank you.
All right, thank you so much.